Thank you so much, everyone. And welcome to my talk, The Inescapable Essence and Extraordinary Beauty of Streaming. It is my great pleasure to be the closing keynote at Functional Scala 2024. We've had so many amazing talks, and I get to be the very last one that you see tonight. Mostly, I like this slot because I can go for as long as I want. I can keep on going and going and going. Christina, you're probably going to have to jump in here and stop me at some point because I have way too much content for 45 minutes. So I'm super excited about the talk tonight, about presenting my ongoing interest and research into streaming. But I have to admit, a little part of me is sad. And that's because I am doing this as a Zoom talk. Functional Scala 2024 was online this year. So I'm doing this as a Zoom talk. And as you may or may not know from some comments I've made in the past, I'm not the biggest fan of Zoom talks. And that's because the experience for a speaker is almost exactly like talking to a wall. There's no one there. There's no one looking at you. There's no one responding to your remarks. There's no eye contact. It is literally exactly the same as me giving a talk to that wall over there, which you can't see, but there's a wall there and it's exactly the same. So what I would like to ask you to do, I'm trying something different in this Zoom talk. I actually have all of you on my phone. I don't know if you can see that, or Zoom's making it disappear. But if you're here, then say hello, right? Let me know that someone is here. Okay, Adam Hearn. Okay, fantastic. I know there's someone out there. Damian Reed. Wow, fantastic. Daniel Vygovsky, David. Wow, fantastic. All right, well, that makes me feel a lot better psychologically that it's not just me and the wall. There's other people out here talking. Fantastic. Now I'm talking to a wall with emojis on it. Just kidding. No, it's way better than that. Thank you for being there and for responding. All right, let me go ahead and kick this thing off. So what are we going to talk about today? Well, we're going to talk about streams, and there may be a few of you who don't know why streams are just such a big thing in the Scala community. I'm going to give you a few reasons why we really like our streaming libraries. And then I'm going to talk about state of the art in the functional Scala ecosystem. The streaming libraries we have are very mature. And also they are very, 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 very complex. And I'm going to dive into some of the reasons why that's the case. And then what I want to do is spend the bulk of this talk trying to extract the core essence of streaming out of this problem domain. And I'm going to end up presenting something that I think is extraordinarily simple and elegant and beautiful, and which truly captures, I believe, all of the essential elements in any streaming library, whether that's Zio streams or Akka streams or FS2 or whatever. And then I'm going to take in the very final segment, and I'm going to say, there's a few things here we can learn, and we can probably turn into working code if we do that in a very careful fashion. So let's go ahead and get started. Streams. Where can we use streams? Well, pretty much anywhere you look in modern day programming, you can, in fact, use streams. You can imagine a server as nothing more than a stream of connections. And you can imagine a request handler as something that takes an incoming stream of bytes and maps it to an outgoing stream of bytes. JSON RPC can be viewed as basically a function from the client's incoming stream of events to the server's outgoing stream of events. Server-side events can also be viewed as a stream of events that are coming out from the server and notifying clients. Relational database systems can be viewed, your input to the database can be viewed as an element in a stream of requests. And then every result set you get out of a relational database can be viewed as a stream of rows from the table that is resulting from your query. NoSQL, same thing there, blob storage, event brokers, analytics, and ML. Wherever you look, there's a ton and ton of applications for this concept of a stream. Now, I'll be honest, 100% of all of the use cases for streams can be done with ordinary loops. This is how the Java guys and C guys before them solved problems since time immemorial. So why in Scala do we really care about our streams and we not want to solve these problems using for loops? And the answer is fourfold. I'm going to give you what I believe are the four most compelling reasons to use a streaming library. And the first one is they're declarative. What does that mean? It means that when you're constructing a data streaming pipeline using a streaming library, you're focusing on the what. You're focusing on information being turned from the raw lines of text into JSON and from the JSON values into this. And then you're focusing on aggregation and then maybe dispatch to multiple different destinations, et cetera. You're focused on expressing that in some sort of data dependency graph. And that's a very high level. And it's very pleasant to work at a high level because then you can more easily understand it and test it. And then what you allow the streaming library to do is to translate that high level declarative description of what you want to do into the low level series of operations that are going to end up making this actually happen in a way that's performant and has all the other nice properties of streaming. So property number one, declarative. Number two, big data. And by that, I don't necessarily mean the Hadoop version of this, but rather just the fact that streaming libraries let you handle an infinite amount of data in a finite amount of memory. So they're built for never-ending amounts of information. They can all handle never-ending amounts of information. So you can use them for requests and responses, where the responses are gigabytes. And you can also use them in open-ended situations like stream processors, where just more information is constantly added and there never ends up being an end to that information like in event-oriented systems. Number three, concurrency. So streaming libraries, unlike for loops, make it very, very simple to introduce concurrency in any part of your data pipeline without having to do a major refactor. You can't do that with a for loop. A for loop is essentially always going to be synchronous. It's never going to be in parallel, and you don't have any control over that. So these streaming libraries give you a knob that says, well, over here, I want to increase the parallelism factor to 10 or 100. And over here, I want to turn it down to maybe 1 because it doesn't make sense to do it over here. And you can make these little tiny adjustments in a way that doesn't actually involve any major changes to your code. It's just a tiny little change. And that allows you to produce very highly scalable and low latency data pipelines and also maintain them over time, because over time you need to add this and you need to remove that, and that changes the types of concurrency decisions that you make. And streaming libraries make it very easy to do that. And then finally, and I don't mean that this is the least concern, far from it. This is actually a very important concern, but it's this property that these streaming libraries have of allowing you to build leak-free systems. What do I mean by leak-free? Well, ordinarily, when you're making calls to remote systems and you're querying databases and you're opening files and you're interacting with Redis entries and so on and so forth, you are creating a lot of resources that have to be released. And if you don't release them, then they're not going to be released until the process itself releases all of them when it ends life. And so you can end up very easily, if you're not careful, leaking resources. And when you leak resources, you eventually mean that your server has to be restarted to continue operation. And I love, maybe love is the wrong word here, but I love that we live in a world where it's not uncommon practice by ops teams to time those server restarts, right? Because they know that after a while, the server starts behaving poorly, so you got to restart that to clear up all these leaks. But in the world of functional programming and in the world of programming languages like Scala that have strong static type systems, we want to do better. We want to actually build systems that never leak. And they never leak no matter what happens. and they never leak no matter how much concurrency there is. And streaming libraries let us do that, unless, of course, they have bugs. What does that look like? Well, here's a very simple pipeline formed from reading some information from a file and decoding it using UTF-8, and then splitting it into a bunch of lines, and then just printing out each line. So this is a very simple pipeline, but you can see the compositionality here of streamings. Streams are enormously compositional. And so you get all these different building blocks, and you can decide how to mix and match them to solve any possible problem. And the solutions that you see, this one included, are just so simple and so elegant and easy to understand, and they're easy to test, and they have a lot of amazing properties. And we get to take the hard work, the hard stuff, like here, there's no opening a resource and closing it, right? There's nothing like that here. We don't have to think about that. And if we wanted concurrency here, we could easily introduce that, right? It would just be a one-liner or less than a one-liner to introduce concurrency. And we have the guarantees that this can work over any amount of data, that it is very high level and declarative, and that it's easy to introduce concurrency. We're not going to have any resource leaks, etc. So this shows you what best in class example use case for streaming looks like. All right, well, that's the upside of streams. There's a downside to streams as well. And I'm going to show you on the next slide. Well, before I do, actually, let me briefly review the very long and very complicated history of Zio streams. And then I'm going to show you a peek into the inside of what Zio streams look like in Zio 2.1, just for your viewing pleasure. So the very first version of Zio streams, written more than 4 years ago, was based on some work in Haskell that is often called iteratees. And iteratees are basically functions, short-circuiting fold functions that can decide whether or not they want more input. And this very simple and elegant concept, it actually turns out you can build a very powerful streaming library on it. And I did that by recognizing that basically continuations are baked into async effect systems like Zio, which gives you the ability to do suspension, which lets you do concurrent operations, even on the very simple version of iteratees that first library shipped with. But there were some drawbacks to that. In particular, the overhead for concurrent operations were very, very high. And even though I love this simplicity and the elegance of that early implementation of Zio streams, the reality was it wasn't very production worthy. There were some very significant performance drawbacks when you started to use this for heavy concurrency. And so we had to go back to the drawing board, and we had to reinvent streams a couple of times before we came out with a very, very interesting version of Zio streams that Itamar Ravid did a lot of the work on. And this was based on the concept of streams being a recipe for describing the construction of an iterator whose get next operator is going to return a functional effect. And that's, I think, one of the most underrated representation of streams that is capable of having extremely high performance for many synchronous workloads, and even some like merging, any sort of conditional merging where it's not concurrent and you're reading like merge sort, for example. You can have incredible performance. And they're very easy to reason about because everyone knows what an iterator is. So it's very easy to get contributors working on these things. They did, however, have some complexity drawbacks for concurrent operations. And ultimately, that's why we decided to go back to the drawing board yet again and reinvent streams again and again and so forth. I know there was one time where we had this really young contributor I was mentoring him, and we were working on Zio streams together, and we would make so much progress, and then we would get to a dead end. We would get to something that wasn't going to perform, or the pieces didn't fit together correctly, or it started to become way too complex, and we had to start again. And we repeated this process 2 or 3 times before he put up his hands in despair and left, and I never saw him again in the Zio ecosystem. He just went off and he went over to type level and started working on that stuff. I felt so bad for his experience, but the reality is streams are not a simple problem. And we had to go through a lot of iterations that we ultimately threw away before we got to the current, well, the one before the current one. Our first introduction of something called channels, which allowed us to unify the stream and the sink and the transformer or pipeline, the three different essential elements of any streaming library. And that work, I think, was very important because it represented a new level of understanding. We understood something deeper because for the first time, we were able to say that these three things, which looked totally different to us, a sink doesn't look like a transformer or pipeline, and that doesn't really look like a stream, where we were able to see that these three distinct things were actually manifestations of a single concept, and that concept was the channel. And then we reinvented channels. We went with a different encoding of that Adam Fraser worked on quite a lot. And Daniel Vygotsky, I think, had a hand with the first version there. And together, I think we brought something quite interesting and innovative to the streaming ecosystem in Scala. However, our story doesn't end there. In fact, if you go and you look into the ZioStreams codebase and ask yourself what a channel is, then you will be staring at an extraordinarily dense wall of text that is actually far more complicated than what I've put on this slide here. I've elided all the details because you would not be able to make sense of everything if you were to see it all here. All the type parameters are gone. Everything's been dramatically simplified. So this is what a channel is. Everyone got that? You ready for your quiz? Yeah, I didn't think so. So I can stare at this. I helped write this code. I can stare at this, and it doesn't matter how long I stare at it. I am never going to come to a deep insight or understanding of what streams are. Deferred upstream, bracket out, bridge, bold. What the heck? Just pipe to, read? No. If this is what a channel is, if this is the simplest thing that a channel can be, then it's beyond my mind. It's just, beyond comprehension. Imagine trying to give a formal semantics to what a channel is, given all these different operators and constructors on them. It would be very, very challenging and very difficult. And I'll talk about some of the implications later, but lest you say, well, this is just ZioStreams. If only you would look at FS2, well, there's FS2 for you. Yeah, so more constructors, more operators, more higher kinded types, more complexity in every possible way. Right? This is even more complicated, right? I don't even know what I'm looking at. I mean, I kind of do because I've looked at the code base before, but this is just, this is a bit much. And this complexity doesn't stop where channel or where pull is defined. It actually seeps its way into all of the operators that are built using these core data types. And here's an example from Zio's map out Zio par unordered operator, which is, I would say, probably mid-range complexity. This is by far not the most complex operator in ZioStreams. So take a look at this. In fact, I don't know if you can see my mouse cursor. I hope you can. Look at some of the stuff that's going on here. Permits with permits on a Zio unit, dot interruptible. So we're making this thing interruptible. And then what? We've got a zip right to outgoing offer exit. What is going on here, right? And then all this is just a tiny little snippet. Dot ignore, and then we're racing first with Z channel await error signal. What the heck is going on here? This is some of the most complicated code to inhabit the entire Zio ecosystem. In fact, there are still fragments of code that survive all the way back to version 2 of ZO streams, the one with the iterators. And I don't know, I don't know if the people who wrote them, including myself, understood them at the time, but I can guarantee you, fast forward 4 years, no one understands them entirely right now. They work. Don't touch them because you might break something. You probably will break something if you touch them. It's just very, very complicated code. And it's not just ZO streams, it's FS2 and Akka streams to a lesser extent. They're just complex. And all of this complexity, it has hidden costs, or maybe they're not so hidden. And one of those costs is just performance regressions. Right? You're in there and you're messing with something, you can tremendously change performance. In fact, you might see a complicated version and you might rewrite that to something that's far simpler and easier to understand and easier to test and maybe fixes some bugs, but you might fundamentally alter the performance characteristics of that code. Or you might introduce a bug. It might be optimizing performance or adding a feature. You might easily introduce a new bug. It's so easy to do. And all of this results in extraordinarily costly maintenance. ZO streams does not change often. And when it does, it sometimes breaks things. And that's just not a great situation to be in. So in the face of all of this complexity, both in these data types and also in the implementation of the operators on these data types, we sometimes have to take a step back and ask, did we take a wrong turn? And that leads me to this next section, essential beauty. So about 2 years ago, I was preparing for a workshop on advanced streams. And my earlier workshop on, beginner or basic streams, it actually looked at ZO streams. But for this workshop, I wanted something different. I wanted to actually give all of the attendees of the workshop insight into how streams work. How can you boil something that is very, very complex down to its essence as a teaching device? So you can understand what a stream is and what sort of operators and what sort of expressivity that stream abstraction entails. And so I spent a lot of time preparing that material and a lot of time basically taking our very complicated streams and chopping them down to size, just ripping out as much as I possibly could from these streaming libraries and getting things down into a manageable size for the workshop. And it was an amazing experience because I had the opportunity, I think, to make some novel learnings for me. I had the ability to really more deeply understand streams. And over the process of teaching that workshop and getting lots of feedback, it just took things to a new level. And I decided, well, someday I'm going to give a talk about this to the Scala audience and present my learnings. And I was going to give a talk a year and a half ago or so, but that didn't work out. So here I am at Functional Scala 2024 giving this talk to you. So what I want to do is start from a blank slate. Rip everything away. Let's just go back to the beginning, go back to the basics, and see if we can incrementally build a stream that is going to satisfy our 4 essential characteristics of streaming libraries, including maybe a new one, which is being beautiful. Our streaming library should be beautiful. And declarative is maybe part of that. It's kind of assumed that anything we would do here anything I would do at Functional Scala is going to be declarative. It's going to be functional. But we want it to be more than just functional. We want it to be beautiful. Because in that beauty will lie a hidden simplicity that is going to not just help us understand this domain more, but also if you push that into production, if you're able to carry it all the way through into a streaming library, then that simplicity is going to help you maintain that code base over the long run and minimize bugs and minimize or maximize the agility with which you can add new features that meet user demands. So that's what we're going to do. And we're going to start with a very, very simple definition of a stream that you see on this slide here. And it says basically a stream is an enum, to use Scala 3 terminology, that has two cases, cons, and cons is that has a historical name coming from Lisp. And a con cell basically just means you have a head there and then you have a tail, which is the rest of the stream. So this con cell is itself a stream. So it's a recursive ADT. And then you have the empty case. So every stream is either a con cell, which contains a head, and then the rest of the stream, or it's an empty stream. And this is a very simple definition of stream, and you can very easily construct a huge number of useful operators on it, like concatenation and mapping and flat mapping, and way more than that, actually. You can do a huge number of things on this, and it's not that hard. It's very easy. This is something that you would do as part of learning Scala or learning how to do functional programming in Scala. You would build a structure like this in order to more deeply understand recursion and the different useful operators you can add to a collection-like entity. And that's it, right? This definition of stream is inherently beautiful. It's beautiful because it's simple. I can understand it. You can understand it. We can test it. Anyone can go into this type of code and maintain it with a modest amount of training. And they're probably not going to be introducing performance regressions or bugs like crazy, just because it's so easy to get your mind around what this definition of a stream is. In fact, it's basically just the one in Scala list, right? This is a list with a different name. This is Scala's singly linked list with a simpler implementation as well. All right, well, that checks the beautiful box. So we have a beautiful stream. And then the next step is how do we make this stream scale to handle any amount of data? Because right now, it only handles an amount of data that will fit in memory. And the reason for that is a stream of A actually holds all of the A's inside it. Because either it's empty or it's cons. If it's con, then there's a head right there. And then the tail is, you have a reference to the tail. So you can peek inside there and see the head of that, et cetera, all the way to the end. So this is a linked list where the contents of the entire list are in memory. So this is not going to work for stream processor type use cases or for big data, any amount of data that won't fit into memory. So our first step is to generalize this to handle any amount of data. How would we do that? Well, look at this, and the simplest possible change you can make that would generalize this to handle any amount of data is actually replacing the head and the tail by function zeros that evaluate to head and tail. This thing here is sometimes called a lazy list. And it's a lazy because if you have a con cell in your hand, you don't yet have either the head or the tail in memory yet. What you have are functions. And these are function zeros, so they're functions that don't take any arguments. And if you call the head function, then it will give you back. It will compute the head. If you call the tail function, it will compute the tail. But it's only going to compute the head and the tail when you call those functions respectively. So this is a fully lazy stream. And even though we've changed the definition of head and tail, the implementation of core operators like concatenation and map and flat map is still very straightforward. It's very easy to implement all these operators and dozens, maybe hundreds of other operators using this very straightforward definition of a lazy stream. So we've moved this data structure from storing everything in memory to describing how to produce head and tail with these function zeros. And that allows us to defer the production of the tail, and maybe the head too, into the future. So what does this mean? It means that we can describe a stream that reads from an infinite Kafka queue. And every time you look into the tail, you get back a new stream. And then you look into the head and you pull out the next element on that queue, on that topic. And then you look into that tail and then you peek in there, et cetera. And you can keep on doing that forever. And so this allows you to describe infinite data. So congratulations with a very simple definition of stream here, just making the head and tail lazy, we are able to scale to handle any amount of data. And I use that Homer Simpson hiding in the bushes because obviously this is maybe not production grade. There's some problems associated with this, some major problems. One is stack safety, but another one is that if we were to use this for any sort of iterator, we would have to work very hard to avoid leaks. And the reason is if we're pulling back a result set from a JDBC, if there's no concept of closing or there's no concept of us being done. So if you're waiting to close the result set until you read every last entry, then which you could do, then you're relying on someone who's using this stream to pull all those elements to the very end. And that might not happen. You can't force a client of a user of this stream to pull to the end. So you're going to introduce leaks in particular when any stream processing code throws an exception or whatever, it's not going to go into the tail and pull the rest out. So you're going to be introducing a leak. So this is not leak-free. It has that major problem. It's also not stack safe. So as you go in here and try to define some of the different operators, you'll find you'll eventually blow the stack because of repeated function zero composition. But that said, this is actually useful enough that at one company, this is a company that existed prior to FS2 or ZIO streams, we actually used something like this. And we made it work. It was a bit of work to get it working, but we made it work and it was very fast and it met our needs for the time. And it's so simple. It's impossible for me not to admire the simplicity and the beauty of this because, hey, if this were to solve your problem, why not use this? Why use something more complicated? All right, well, this stream is not concurrent. So we can't do things concurrently. We can't say, oh, we want to do some processing on batches of 5 elements all concurrently and then group them together in a subsequent stream. It's impossible to say that. And the reason for that is it's not possible to do anything in an async way unless you're running on Loom. You can't execute head or tail in a concurrent way without blocking threads. And we don't want to do that. We don't want to block threads in Scala.js, Scala native, and pre-Loom versions of the Java virtual machine. So this is not going to cut it if we want concurrency. And even if we're running on Loom, we might be able to stuff concurrency into this basic framework here. But probably it's going to have overhead. It's for sure going to have overhead. And also, we're not going to get the sort of knobs that we might like if we want to refine like parallelism number and other types of things in a very easy way. So what should we do here? Well, does anyone know the name of a Scala library that is designed to solve problems in asynchronicity and concurrency? Well, of course, there's plenty of them, right? ZIO, yes. And there's Cat's Effect, and there's Kyo, and there's all sorts of libraries out there that are designed to help you solve problems like this. And so if you look here at the head and the tail, they look a bit like a functional effect, right? Functional effects describe how to produce values. And here for head, we have a description of how to make an A. And here for tail, we have a description of how to make a stream of A's. So they look a bit like functional effects. And so the first thing you might say is, well, let's just replace that A or that function 0 of an A by a ZIO effect and replace that function 0 for the tail by a functional effect and see what happens. It turns out you actually can't make that work. The types don't allow it. There's some operators you just can't implement. So I'm going to show you what I believe is probably the simplest possible way to make that work. Basically, take the head out and stuff in a functional effect there. And in making these changes to stream, we're going to be moving away from the world in which stream is a simple data structure and into this new world where stream becomes a description of a streaming process. Okay, so list and our original stream was, no doubt about it, pure data. When we introduced the function zeros, we move from pure data to something called codata. So we move from data to a process. And then as we move from the very simple definition of stream that you saw in the preceding slide to this one here, we're moving from a simple process into one that is more faithfully reflecting the structure of stream processing. So I'll explain each of these different constructors for stream in turn, but keep in mind here that the big shift you have to wrap your mind around is that this is no longer a data structure. We are actually describing operators inside the streaming domain with these constructors. And that has some implications that are going to complicate things later on. A first constructor we have is emit. And emit describes the production of a value of type A. And how I decided to do that, there's lots of ways we could do that, but how I decided to do that is to just stick a zero effect in there. This is our new head. It's not exactly, it is not exactly cons, but it is the head part of cons pulled out and wrapped into a functional effect. So this emit is, okay, we want this stream to emit the value whose construction is described by this effect. And that represents one of the ways of building a stream of A. So for example, if we had a function that could read some bytes from a socket, then we could call that function inside a zero effect. Then we could take that effect, we could bundle it in here, and now we have a stream representing the reading of those bytes from the socket. The next operator we need, this actually turns out to be the fundamental one, whose absence would give us major trouble if we were to try to just take the other version and zeroify it, is this flatten operator. And the flatten operator says that if we have a stream of streams, then we can somehow flatten that down to be a stream. And this arises from the monadic nature of streams. So streams support flat map. You can use them in 4 comprehensions. And it's very, very useful because many times when you're doing a streaming computation, you have all your input elements, right? And you want to take one input element and you want to feed it into a new process, which is going to generate a new stream of things. And then you want to take those, every element there, and you want to feed that into a new stream and so forth. And you keep on doing this. And this is flat map. And so in order to have that power, you need something like this flatten operator here. And then there's concat, which is serving the purpose, or at least 1/2 of the purpose of the old cons. The old con cell said, here's the head and here's the tail. And so that cons is actually a combination of 2 things, emitting the head and then concatenating that simple singleton stream with the remainder, the right-hand side stream. So I chose, because it makes things very simpler, or very much simpler when you choose to do this, I chose to separate those 2 functions and say, okay, we have the head over here, or just a singleton stream here, and then you can concatenate that singleton stream with any other stream that you want. So this is concatenation, stream concatenation. And stream concatenation is lazy on the right-hand side. And I did this so we can allow you to build infinite streams, basically, out of concat, which is important because we said we would allow you to describe infinite streams. So if that were strict, we would not easily be able to do that. We would be able to do it through emit, but this is a much more direct encoding of that concept. And then finally, we have the empty stream. All right, so this is 4 constructors of stream. So we're saying every possible stream in the world is either emit, flatten, concat, or empty. And we've got a zero effect stuck in the middle of here. Is this true? Could this be true? Well, not only is it true, but surprisingly, well, let me just show you some of the basic operators here. Okay, I'm cheating on concatenation and flat map because those are just taking the left and right hand parameters, and they're stuffing them into one of these data structures. So we're describing the streaming computation inside our stream data structure, but we're not actually doing any work. So we've not yet fully solved the streaming problem. What we actually need to do something more. And that something more is we have a stream of A that is very abstract now. It's no longer just a cons and an empty. We have all these intermediate things that are describing streaming processes. We have to take a step back and say, well, what can I do with the stream? I can no longer just pattern match on a stream and get the head out and do something with it and then continue on with the tail. Stream is too complex to allow me to pattern match anymore. So in order to reconstruct the ability to pattern match on that simple stream, we need to implement an operation that is sometimes called uncons. And cons takes a head and a tail and sticks them together in a stream. Uncons takes a stream and pulls out the head and pulls out the tail. This is the most fundamental operation that you can implement for a streaming library. And I'll even go one step further. If you can't implement this, and there are streaming libraries that can't implement this, then it's going to be a massive source of pain for implementing new operators. Right? Fundamentally, we need the ability to take an element and prepend that onto the rest of the stream. We can't escape that. But also, if we want to transform streams, we need the ability to take a stream and pull an element off and get the remainder and then do computation. So I'm going to argue here that any streaming library, as a sort of litmus test for its expressivity, should support cons and uncons. Now, uncons might not have a very good implementation. It might be very slow, and there are reasons for that I don't have enough time to cover today. But if you can't do uncons at all, there's a major problem. So we need to do uncons. If we do uncons, then it is proof that we could build, basically, because we can already do cons, right? It's obvious how you do cons using these operators. You just emit something and you concatenate that with the right-hand side, which contains your remainder. So you can do cons, you can build streams, any possible stream you could build. If we can do uncons, then we can deconstruct any possible stream. And if we can construct streams and if we can tear them down, then we can transform them. So basically, we can do all the stream things. Right? That's the beauty of this compositional reasoning, is if we can construct a stream and we can tear it down, we can do all the stream things. There's nothing we can't do. And the use of zero effect here actually gives us a very important capability I'll show you in a second. So this is the beast that we need to implement if we're going to prove that our stream is fully expressive. It's uncons, and it gives you back not a head and a tail, but an effect, and that should make sense, right? Because we've allowed the production of the head to involve functional effects. It could be concurrent or asynchronous. It could be talking to the outside world. It could potentially fail. So that's going to leak into the definition of uncons. We can no longer do pattern matching. And that should make sense because we don't have that data in memory. But we can say, basically, give you the next best thing to a pattern match, which is, okay, run this uncons effect, and then you're going to get back an option. Why option? Because the stream might be empty. That's not an error case. It might be empty. But if it's not empty, then you're going to get a tuple, and that tuple will be the head and the tail that you're looking for. So uncons is the opposite of cons. And the only difference here is that instead of pattern matching to tear down our stream, we're having to call this as a function and get it back into somewhat complicated looking data structure. If we can implement this, then we'll have proven that this is a very expressive, powerful definition of a stream, even though it's very tiny. How do we do this? Well, in the emit case, it's very simple. We have a value already, and we don't have a tail. So we take that zero effect, and we map over that zero effect, and we turn it into a an A and then an empty tail. The flattened case is actually ridiculously complicated. It's ridiculously complicated. And if you understand this, then you'll understand the whole principle by which this sort of micro stream works. What happens is the case here is we have a stream of streams of A. Okay, so we need to get an A out of that. If you look at the type signatures, you'll come to the conclusion that you're given a stream of A, and you have to get an A out of that as well as the remainder. How does that work? Well, there's really only one thing you can do at that top level, and that's to try to uncons the stream of streams. This is the nested stream. We uncons that, and there's two possibilities. There's a none here, and there's a sum. None represents the case that our stream of streams is empty. So if our stream of streams is empty, that means there's no more inner streams left, right? There's no more inner streams. So it means we can never get any more A's out. So we just succeed with none. So that's that none right there. And then in the sum case, we have a head, which is, keep in mind, because we're dealing with a stream of streams, our head is actually a stream of A's. And the tail is a stream of A's. So what are we going to do? Well, with the head, we're going to take the head, and we are going to uncons it. And there's two possibilities. Either there's nothing left, in which case we're going to recurse. And we're going to recurse by taking this stream of A's and wrapping it in flatten, and then calling uncons on that. Why do we have to wrap it in flatten? Because we need to convert it from a stream of A into a stream of A, which we do by using that constructor. And then we uncons that, so we can end up getting back our single A. We don't want to uncons a stream of A's because we would get back the wrong type. So basically, we just handle this case through recursion. And then in the case that this inner stream has an element left, then we do this very complicated transform here. We peel out the A, and that goes into sum. And then we still have these remainder A's. So what we do is we take the remainder A's and we succeed with them, and we emit them, and then we flatten that. And what this is going to do is, this is our stream of A's. Once we emit this, we're going to end up with a stream of A's. And we're going to flatten that down to a stream of A's and concatenate that with the nested remainder here that we got out of calling nested.uncons. Very complicated. So we have our stream of streams. We pull out that first stream. You know, if we're empty, we're done. But then we pull out that first stream. We have our remainder stream of streams. And then we try to pull the A out. If there's no A out, then we just recurse. If there was an A, then we hold on to that A, and we take this stream of A's and we bundle it into a stream of A's, a singleton stream of A's. And then we pre-pen that to all the nested stream of A's, the remainder down there. And then that becomes our continuation stream. It becomes everything we've not looked at so far. Does that make sense? Okay. And then we have concat case, which is way simpler. We just uncons the left, and if there's nothing left there, we just flip over to the right-hand side and we uncons that. But if there is something left, then we take that A, and then we still have some leftover A's from the left-hand side, so we have to pre-pen those leftover A's to the right-hand side. Okay, so we have leftover A's that we've got to say are part of our remainder. So we take that remainder and we concatenate that to the right-hand side. This one I think is much easier to understand. And then if it's empty, of course, we just succeed with none. So what is this doing? Well, the high-level way to think about this is we have this big, gigantic structure representing our streaming computation. And it has flatten inside there and concat, and those are nested however many levels deep. What we're doing is we're performing a search of this to find an A. We're trying to pull out an A. And so we go down as far as we need to in order to extract an A. And we do that by deconstructing these flattens and these concats and so forth until we get to that A that we need. Once we find that A that we need, we then reconstruct the structure of the stream, right? We build it up again, and we return that as the remainder. So if you're familiar with a zipper, it's a kind of like, zipping into this part and then pulling something out and then zipping it back up again, and then that becomes the remainder. And it's not strictly a zipping operation because we're forgetting things. Right here in the concat case, if there's nothing on the left-hand side, we forget that. And also in the case where the flattening is done, we forget that, we throw away structure. So we are genuinely getting rid of stuff when we can, but to the extent necessary, we are not just breaking stuff down, but building them back up again to preserve that remainder to make sure we don't lose any of the information that is inside the stream. All right. Wow. Well, I am going to now try to do a little hand wave and convince you that this definition of stream is fully concurrent. That is, you could implement any possible concurrent operator ever with this very simple definition of stream. All because we chose to stuff a ZO effect in there. A ZO effect only occurs in one place. It's emit. That's it. That's all the ZO-isms here. That is enough to allow you to implement any possible concurrent operation you want. How do I convince you of this? Well, I write into Q. Okay? And into Q, what it does is it takes the ZOQ, which is async, concurrent, all that good stuff, and it transforms this stream into this queue. And what that allows you to do is if you can turn streams into queues, then you can pull from those queues in any way you want. And so you can do concurrent merges according to whatever criteria you want. And in fact, in early versions of ZO streams, like the iterator version, for example, we used queues a lot. We basically use queues in order to implement concurrent operators. So this is not uncommon. It's quite common. And I'm not necessarily saying that you would need to stop here. If you wanted to provide more built-in support for concurrency, you could, but you don't need to. And the reason is this is 4 lines of code, 4, that turns this stream into a queue, which therefore demonstrates any concurrent operator you want to implement, you could implement in terms of these queues. So what does this mean? It means that our 4 constructor stream is fully concurrent. You can do anything you want with this. Anything you can do with ZO, including racing and parallel, all that fun stuff, you can, in fact, do with this stream. That's amazing. That is really amazing. Because I've never seen a stream that was this simple that allowed you to do all of these different things. However, we do have a problem. And that problem is quite significant. And it's the problem of resources. So real world streams, they allocate stuff. They open connections, they make requests, they hold on to those connections as you're pulling elements out. And eventually these resources, they have to be cleaned up. And there's a way that you can describe cleanup using this structure here. I could show it to you, actually. It would take a few lines of code to show it to you, but you could do it. However, you would not have any guarantees in the presence of errors, stream errors. So this structure is not sufficient to guarantee resource cleanup. You can do like happy path cleanup of resources using this, but that's it. In order to do unhappy and happy path handling of resources, we have to change this in some fashion. And the dumbest thing you could possibly do, we've been trying pretty dumb things, right? Our first thing was, well, let's start with a list. It seems good enough. Let's just make it be able to handle big data. And so we made it lazy. And then we're like, well, it's not concurrent. Let's stuff a ZO effect in there. And so the dumbest possible thing we could do here is stuff a resourceful ZO effect into the value of emit. Right? Could there be anything more dumb than that? I don't think so. Could that possibly work? It doesn't seem like it could work. It seems too complicated. Well, here's the definition of uncons. There it is. I mean, I've refactored this a little bit. I had to switch over to using the real ZO. Cal pointed out, or Adam pointed out astutely, that I was using task succeed. That's because in the other one, it was a toy one I did as a side project. I wrote my own task. This has now switched over to the real ZO, so I cleaned up some of the type signatures. I like this version better. But there's really no substantial changes here. It's pretty much the same. And that's amazing. However, don't jump to the conclusion that this means we're done. We are most certainly not done yet. Even though this compiles, and even though it won't leak resources from one point of view, I guess, the reality is that every resource that is allocated over the course of pulling these A's out will remain fully allocated until you are completely done with all of the A's. Okay? Ultimately, you get this scope in the environment here, and you're going to have to use ZO scope to eliminate that, which is going to clear up all the finalizers that were installed over the course of the streaming computation. This, in general, is not what you want. It's not what you want. And that's because as part of a top-level stream, you might be reading from a queue, but then as part of that stream, you might map every one of that into another stream that represents requests. And so that's going to be a different stream, and it should have a different lifetime. And it would not be correct, at least it would not be efficient. You might not conceptually leak resources, but still you're holding on to them for too long, which is the same thing. In fact, if your top-level stream is designed to never end, then basically it matters very little that when you kill the process, everything is going to be freed, because that's too late. Your process is designed to run forever, and so you need to eagerly release things at just the exact right moment in time. And it's not so simple. It's actually quite complex. Here's a stream of A. Stream of A emits these A's at regular intervals, and then you might be allocating as you're going, right? You might be actually establishing connections with databases or whatever. Probably for the first element, that's when you talk to the database, you get a connection or whatever, and you make your query, and then you get back your first result. Okay, great, you've allocated a resource. And now you're going to keep on pulling that until the end of the stream. And then when you get to the end, or when an error occurs, you need to release. But that is not the same as, like, let's say I talk to a database and I get back those results. And then I talk to a local cache and I get back those results. And then I talk to DynamoDB and I get back some more results. And I want to concatenate them all together. How should that work? That should work differently. It should be the case that as I exhaust all the relational database entries and I get to the cached entries, that I close the connection to the database. And then when I'm done with the cached entries and move on to the DynamoDB entries, I should close the Redis connection, etc. So we want to do early release in that concatenation scenario that I mentioned. And then furthermore, if we have something like a stream of A's, then we have the outer stream, which could be allocating its own resources, but then each inner stream could be allocating resources that could be safely freed when those streams come to their natural end, either by producing their last value or through some sort of error condition. Okay, so that simple definition that we came up with in this previous slide, as alluring as it is, and as surprising that it's, actually is resource safe, at least in the sense of the top level stream always deallocating any resource allocated by any substream, it's not enough. It's not really the definition of leak free that we're looking for. So what can we do? Well, it's not obvious. Look at this. Like, this is probably the main problem with building a streaming library. Concurrency is hard, and I don't mean to say that that's easy, but not leaking resources is also extraordinarily hard. You have an interpreter like this, which is doing the uncons, it's giving you an A and the remainder, and you have to consider where should we release which resource, and how should we describe that? How should we talk about that? And also, like, even if we knew where to release something, let's say we knew that we should release the left-hand side when we run out of entries. Okay, that would be an approximation to the truth. It's not actually true, but it would be an approximation to the truth. How would we do that here? How would we, because right now this is in Zio, how would we in Zio incorporate this notion of boundary and say, okay, well, we're going to allocate the resources here, and then we're going to free them here at this boundary. The boundaries are at the level of streams, but our code is at the level of Zio, at the level of effects. So this is a problem that all the functional streaming libraries have, FS2 and Zio streams, etc. It's how do we map from this notion of a stream scope to a Zio scope? It's not obvious what to do. So I found a way to do it, and it's surprisingly simple. It starts with the conceptual model, and then I'll tell you how we actually make this happen on cons. But the conceptual model is simple. We'll just say, well, you can already emit a Zio effect that uses resources, right? Because that will just mean that your Zio effect has scope in the environment. Okay, well, do it, right? Do it. If you need to acquire something, just stick it in emit. That's fine. But we also need to have some notion of stream boundary. So we're going to add a second operator called close. And for now, just ignore this. Ignore this Boolean. Focus on this part here. This part here is saying what close does is it's a unary operator that takes a stream that has scope inside its environment and it eliminates it. This is the stream version of Zio.scoped. Okay, it's going to take a stream that's using resources, and which you can see it's using resources, and it's going to say we are going to provide its scope and make sure that when execution of this stream terminates, either on the happy path or unhappy path, we're going to free all the resources right then and there. And this allows you to go along and like have lots of different elements that are acquiring stuff. You're just concatenating them together. And then when you're done using that resource and you've bundled that up into some sort of stream, which is now reflecting the fact that it's resourceful in its environment, you're going to say, okay, well, when this stream comes to end its life, I want to free all of those resources. And you just call close on it. I added this little syntax here, which lets you call close on a stream. And it looks like this. So here I have an effect that opens a file. And then I take that file, I flat map over that file, and I form a stream here by reading chunks. And I just succeed with those chunks. And then I do that in a loop forever until I encounter, some sort of failure, and then I return the empty stream. So basically here I've got this stream that is the concatenation of all these individual chunks. It is in fact allocating information. I have that reflected here in the Zio effect, which quickly becomes a Z stream over here. And I return that on here. I have to use these operators. So what I get out of this entire block is a Z stream that has scope in the environment. I call .close on it, and boom, it eliminates scope from the environment. Now I have a self-contained stream, all of whose finalizers will be executed when the evaluation of the elements of that stream concludes, either for positive or negative reasons. All right, that's the model. That's the high-level semantics, and it's quite clean. It's quite elegant. It's unambiguous. This thing has unambiguous semantics, and it's flexible enough to do all the types of things that you would want to do. Sometimes you construct little fragments of streams that that are going to be using the same resource, and so you want them to share these resources. But then when you're done, when you've composed them all together, like I have in this example, you want to say, okay, now we're done with that resource. We don't want any resources allocated inside here to outlive it, so we're going to close it off. Now, no operator exists without its dual. So there's a dual here to close, which would be open, or you can think of close as being contraction of scope. You have scope appearing in the environment of the streams, and you contract it, you subsume that inside the stream, and now it's self-contained. The dual of that operation would be open or extend. It would be a way to extend a scope. And I think to do all possible things that you would ever want to do, you might need open as well. I did not sketch that up, but it's interesting. It probably needs more research. But the close, I think, is fundamental and very important to ensure resource safety. All right, so to do this, to pull this off, we actually need something that's not been done before, and that is a new type of scope. So scope is built into Zio, and it has a way to add finalizers. But what we need for this definition of stream is a sort of frame of scopes. And so this is going to be a type of scope that allows you to push new frames on and pop them off. And I just extended scope here directly with push and pop. And the meaning of these things are you push on a new scope, and now every time you call add finalizer, it goes onto the new scope. And the new scope could be closed when its parent is closed, obviously, but it will also be closed when you call pop. So when you call pop, it will close all of the finalizers that were attached on that frame scope. And then in addition to that, well, actually, that's all really you need is uncons needs to use a new stream scope. And then the definition of uncons becomes as follows. First off, I define two helper functions, which are just designed to push and pop a new scope onto this frame of scopes. And some of these operations don't change at all. The interesting ones that do change are close. Well, close didn't exist before, so we have to handle close. And what does close do? Well, close, this is, whenever you use close, it actually uses the close constructor with a Boolean variable here set to false. So this means the first time that you're unconsing this stream, which is a close, it's a closed node. The first time you uncons that closed node, you're going to push on a new scope onto that frame of scopes. And then you're going to proceed, which is it's not something that can fail. And then you're going to proceed to uncons that stream. And you're going to attach to this effect a finalizer that will cause pop to occur. And what this does is it says, well, we're going to uncons from this type of Z-stream node for the first time. And what we're going to do is set up a new frame, which in the event of an error, we're going to pop off. And we end up reconstructing. So when we're returning our head and tail, we reconstruct close, but we change that Boolean variable from false to true, saying this is now open. We've actually opened this, and therefore we don't need to we don't need to attach a finalizer in the future. And then we go through the next case, which does the case where the stream is already open. We just cons this cell, and we reconstruct the close. So what we're doing here is we're using this ADT in order to maintain the state of our interpreter. And we can stick anything we want in there. Maybe a Boolean variable ends up not being sufficient. I suspect it is definitely not sufficient for a concurrent scenario in which we had some built-in concurrency here in the stream ADT. But we can do whatever we want here. Because this process of unconsing an element from this stream deconstructs everything and then reconstructs it back up, we're allowed to change the state of our observed data structures and to reflect things that have been opened and closed here. And what this allows us to do is to precisely say that we're going to close this stream when we've exhausted all elements inside this stream. So the time where we uncons this and there's nothing left, we've hit the end, or maybe we encountered an error, we're able to close the resources associated with that. And then if the whole thing blows up due to some catastrophic error, we still have this stack of frames that will be closed at the top level when the entire scope closes out. So we're building up this stack, which is linear. As we're going into and out of the structure, the stack might grow and shrink, et cetera, as we're iterating all of these over all these different substreams. So this is not concurrent. This is just singular, or rather sequential. But it does allow us to have that guarantee that no matter what happens, ultimately, because all of these scopes are tied together, there will be no leaked resources. All right, so there it is. A simple definition of streams that is only 1, 2, 3, 4, 5 different cases. We have 5 constructors here. And these 5 constructors allow us to process any amount of data, do any amount of concurrency, and not leak any resources. And I think that's as close to beautiful as you're going to get if you're in a very complicated problem domain like this. This definition of a stream, it's tractable. We can actually do something about it, right? We can, through obviously good tests and verification, we can say, okay, we're not going to leak resources. Anything substantially more complicated than this, though, and we're starting to get into territory similar to the existing ZS streams. All right, well, what about sinks, pipelines, and channels? Well, we've known for some time that there are alternate formulations of sinks and pipelines. In particular, a sink could be viewed as something that accepts a single element and either returns a signal, give me more, or I'm done. That's an iterative. But there's also another way to view a sink, which is, I think, uniquely suited to this representation of stream, which is give me a stream as an input, and I'll give you, and I'm sorry, there's a typo in this slide. I changed this last minute. That should be stream. Give me a stream as input, and I will give you a value that I am parsing out from that stream, as well as the remainder of the stream. What does that sound like? Well, it sounds like a parser. A parser is a thing that, given a string, will give you some value of type A or an error, as well as the remainder of the string. We can actually, with a definition of uncons for our stream, we can write a sink as an ordinary parser. You give it a stream, it produces a value, it produces the remainder of the stream. And that really allows you to see a sink is nothing more than a parser on streams. How about pipelines? Well, a pipeline, this is something we have known for some time. This is not new. A pipeline can be viewed as a transformation of one stream into another stream. In fact, if I'm not mistaken, I think we did this at some point. At some representation, we actually had a pipeline as being a transformation from one stream to another. So this is what it looks like. Your fundamental operator here is transform, and you're saying, hey, I can turn this stream of this one element type and one error type into the stream of this other element type and maybe other element type or error type. And the fundamental operator you can do on those is composition. You can compose pipelines, which is just function composition. How about channels, though? Channels are the hardest to reason about and the most complicated data type. They have actually 1, 2, 3, 4, 5, 6, 7 type parameters. And that's because channels read from an upstream source and write to a downstream source. And I spent a lot of time trying to think about if there's some more essential nature of a channel. Because right now in ZO streams, a channel is the basis of everything, right? A channel is how we make streams, and it's how we make pipelines, and it's how we make sinks. But a channel is a very complicated thing. And what I really want to do is to break a channel down into something that's simpler and say, okay, well, that's the fundamental core thing. And I really tried to do that with channel. I tried to break it down into a transformation from one type of stream, which fails with an error or a done value, into another type of stream, which fails with a different error and different done value. And it's almost there. You can see the basic aspect. If you've used Z channel before, you can see the basic aspects of a channel here. You have the ability to pull input errors and input elements and input done values, and then turn them into output errors and output elements and output done values. So you do have that ability, but there's something different. There's something subtly different about this. And it's that when you read from upstream, you are always going to get something, right? When you call that channel read with constructor, you're always going to get something. You're going to get either an element from the upstream or an error from the upstream or a done value. You'll get one of those three things. It's guaranteed. And that's not true with this definition. I went to implement some of the operators here for a Z channel and I couldn't do it. And the fundamental problem was I have to deal with this empty case, right? You try to get something from the stream, but there's nothing in it, right? So what that means is channel cannot be implemented in terms of stream. Wow. So that means that stream is not fundamental, right? If channel cannot be implemented in terms of stream, then stream is not the primitive over which everything else could be implemented in terms of. So what does that mean? Well, it means that you could say, well, channels are just always different, and they're always going to be different. And we're not going to try to unify them. And maybe we're going to have new streams, which are using new encoding that's easier to reason about, easier to test, et cetera. And we're going to use those over in this world. But anytime you use a channel, you're going to be off using this very channel-specific machinery. And that's not very satisfying. So what I instead did is I played around with an alternate formulation of streams. Fundamentally, the problem here comes from a stream that could be empty. What if your streams could never be empty? What if every stream contained either some number, perhaps infinite number of A's, followed by a single error value, right? Error doesn't have to mean error. As you saw in the preceding slide, you can stick an either in there, and you can say, well, it could be a real error or it could be a done value. In functional programming, this error channel, it just means short circuiting. It means early return. And oftentimes we use early return for error so much that we think, oh, this is always an error, but it doesn't have to be an error. The functional effect of exceptions is nothing more than early return. It's short circuiting. And so we can co-opt this error channel to say, well, we're either going to be done with some value or we're going to get error with some value. But until we make an E, which is this either type, we're going to continuously produce A's. So we have some number of A's, perhaps infinite, followed by a single E, which is the terminal case of the stream. This is an infinite stream that can fail, or early return, or short circuit. And I went down this path, and I ran into trouble with some of the operators like plus plus, concatenation. And the reason for this trouble is that even though logically we only need one channel to represent a stream being done, still to implement some operators like plus plus, we need to know if this is a good kind of done or a bad kind of done. Is this done in a good way, meaning there's nothing left in that stream, and we just want to go on to the next stream in our concatenation? Or is this done in a bad way, in which case we want to propagate that error value? And so what I think you have to do is you have to change the definition of stream here. You have to add a new type parameter. And your fully baked definition of stream becomes one that requires an environment and can end with either an error of type error or a done value of type done, or emits zero or more elements of type element. This is a terminating stream, right? It's just a stream. It's not more complex than a stream, but it is a stream that when it is done will either end with an error value or end with a success value. That's it. And using this definition of stream, it is possible to implement classic ZO streams, ZO syncs, ZO pipelines, the old transformers, and also ZO channels. So in other words, and this, I think many of you would look at this and say, okay, well, 4 type parameters, that's maybe not something to be super proud of, but I don't mind 4 type parameters. However, 7, 8, 9, 10, 11, we're starting to get too many type parameters even for me. I think most people would look at this and say, 4 type parameters, it's not the end of the world. It's not that bad, and it is much simpler than Z channel. And this abstraction here could be the basis of something that would allow us to implement all other possible things in something that could, in theory, be as simple as 5 different constructors. All right, so what about performance? Well, there's a dark side to this in coding, and that is it's not particularly fast. And the reason for that goes back to why it's so elegant. Right? It's so elegant because what you're doing in order to pull the next element is you're deconstructing this structure and you're pulling your 1A out, and then you're sealing it back up again. And then that becomes the remainder. So you just drive into there, grab your A, zoom out, and then hand it off. Very elegant, very beautiful, allows you to store state inside this this tree-like structure, which is how you do resource safety. But also, it does involve deconstructing, which is almost free, but not quite free, because we have all the uncons. So they return zero effects. So they have to go through flat map. And then we have the cost of building these structures, which involve allocation. So every time we've got this plus plus, we're allocating. Every time we've got flatten, we're allocating, et cetera. So we're deconstructing them through zero effects, and then we're reconstructing them through ordinary sort of constructor heap allocation. And that's going to be overhead. To pull a single element out of one of these streams might involve, it depends on how deeply nested this is. It could be a small chain or it could be a long chain, but it's going to involve some number of allocations. So we're not at the point where we can like pull one element out and only allocate 3 things. You pull one element out and you might allocate 10 things, right? And you might have to go through several different ZO operators. So this is still not necessarily a high performance encoding. I still think it's extraordinarily interesting to have a tiny encoding that can be verified to be correct and is simple enough that anyone can work on. But I think if you're not using chunking, right? If you're using chunking, okay, this overhead probably won't be measurable. But if you're not using chunking, you will be able to see this overhead. And you have to ask, what are you going to do about that? I think there's 3 possibilities here. And the first one is basically using macros and trying to do 2 different types of optimizations. One is inlining and another is specialization. I think you could potentially specialize a lot of operations programmatically at compile time using macros in order to significantly improve performance. And inlining can help you because the JVM can do something called escape analysis. So if it does a heap allocation that's only used locally, it can actually optimize that away and not allocate that on the heap. And that improves performance quite a lot. So you get that when you do basically aggressive inlining because more and more stuff becomes local. So escape analysis applies to more and more stuff. So I think some combination of just ordinary inlining through macros and then some sort of macro-based specialization that could eliminate the overhead of certain types of combinations of operators could be very interesting to investigate. I also think the old iterator-based encoding has a lot of promise. I think you still have to fundamentally deal with the fact that concurrency is not trivial in that representation, but there may be ways to mitigate that. I think there are ways to mitigate that. And revisiting this older encoding with some of these new ideas and new insights could be very interesting. It's really hard to escape the incredible elegance of getting your next element just by executing a single ZO effect. That's which it could be async, it could be sync, it doesn't matter. It unifies over both of those. That core idea of give me the next thing, just being an effect that you keep on calling again and again and again is very powerful. So I think there might be something there that's worth exploring. And then finally, I think that if you're willing to change the API, and also if you're willing to sacrifice stack safety, then you can actually choose to represent a simple algebra like this using queues. And that might open up the door to other types of optimizations. One of the big performance bottlenecks that occurs in these streaming libraries is the flat map. Because the flat map says you're going to take an A and you're going to turn that into another stream. So any sort of encoding or optimization you've done has to be redone for every element that you get. And obviously there's going to be allocation there, but then there's going to be interpretive overhead as well. So what you really want is you want to be in a situation where you can have as static a graph topology as possible with no allocations. And then you just want to pipe things through here. Okay, and that would lend itself to a queue-based implementation. You would be able to do some fast pathing optimizations for things already available. Maybe they don't even have to be in a Zio effect, and they're just fast path down through the data processing pipeline. And then if they're not available yet, then they go to an effect, et cetera. So I'm very interested in exploring that. However, that would radically change the API. Any attempt to use queues as the fundamental basis of these few different operators would quite significantly change the API. And if you changed it that much, then you would want to open the door to changing it in any way. You would want to reevaluate everything. You would want to look at the monadic nature of streams and say, maybe that's a mistake. Maybe there's some other way to get at those use cases, which are very valid use cases, which is more compatible with the static topology. And you would want to avoid going down the Akka streams path, not because it's not great technology, it's great technology. It's just hard to use and not very compositional. So you would want to try to get as compositional as you could while still benefiting from as static a topology for your data processing as possible. All right, so lessons and directions. Well, streaming, we want it, we need it, right? We want it, we need it. And I've become convinced by playing around with these sort of toy versions and by my work in teaching the fundamental essence of streams that we can get a lot closer to the holy grail of streaming than we have in the past. I don't think that there's any reason why we need 20 different constructors for Z channel or 25 or 30 for pole in FS2. I don't think we need all 30. I think we can boil that down to something that's a tiny fraction of the size. And I also think we can do that using a new conceptual model that is going to enable ordinary non-genius streaming geniuses to introduce new operators in a sane way without the code becoming too complex and too prone to performance regressions or to bug regressions to keep that cost of maintenance lower. However, despite the fact, I am also convinced that the existing encodings are not going to cut it. In fact, not only are the existing codings not going to cut it, but it's not going to be possible to implement something this radical and this new in a way that's backward compatible. So what do we do? Are we stuck? Especially with this post I just came out with, Zio in 2025. Are we stuck forever with Z channel and its 7 type parameters and it's 20 cases and it's very complicated interpreter? I don't think we are. I think in 2025, we can actually do much better than that. How? A new package, Zio.streams2. Okay, Zio.streams2, written in light of all of the work and the research and experiments that have been done from the Z channel encoding until now. Or yeah, maybe it should be streams 3, Zio.streams 3. Or maybe it should be 4. If we want to reflect all of the failed intermediate versions that we worked on, maybe it should be Zio stream 7. But anyway, a brand new encoding with no restrictions, no limitations, no commitments to backward compatibility in that new encoding, and no commitments even to making the stream a monad. Right? All of these assumptions should be reevaluated in light of our desire to achieve something that's very, very beautiful and declarative and elegant and compatible with big data and highly concurrent and leak-free and all of that stuff plus performance. And what we can do is do that in a way that doesn't break existing code. So continue to maintain and enhance existing Zio streams, introduce this new package with the new encoding, and have bidirectional conversions from the new streams to the old streams. Okay, if this new thing is really as powerful as all the old things, then we should be able to convert in both directions without loss of information. There would be some overhead in the conversion, but it would help get people over the hump. This would allow us to introduce a new type of streaming library in a way that's not going to actually break any code out there in the wild. And then this allows ecosystem libraries like ZOHTTP and whatnot to do upgrades at their own pace. They don't have to use the new streams, but users can use the new streams. Or a library can go ahead and say, hey, we're going to take the plunge here and we're going to use ZeoStreams too. And you don't have to do that because you can just take all the streams too that you get back from this library and you can convert it to the existing streams. So I really think in a library as mature and as sort of, widely used in production as ZO2, and also with our goals to become the enterprise effect system and not break backward compatibility, even though we've got new, fun, cool ideas, I think this is the best path forward. So I think stay tuned for more. I'm going to publish the code. I'm going to clean up and test the code I've written here. There's a few bugs in it currently that I noticed today. I'm going to clean up and fix those. I'll publish that, and then that will be the start of a discussion that I hope leads to a brand new encoding for ZeoStreams that's way cleaner, way simpler, way more beautiful than anything that's ever been seen before, and yet achieves all of the goals that we have in a streaming library.